Haha, I remembered to hit record. Okay, so here's the deal with this chapter, you guys. Honestly, concept-wise, we're really not learning anything new. Everything that we're going to be doing this chapter is just a harder version of what we just finished doing. Okay? The last chapter was Newton's law, so we did, forces and stuff. All of the forces that we dealt with were either horizontal or vertical. All right? The chapter prior to last, we did vectors, in which we dealt with velocities and accelerations and forces that were at weird angles. All right, so that's really all we're doing here is we're going to take the little bit that we learned about vectors in chapter 3 and combine it with, or I guess it's chapter 2, right? Combine it with what we learned about forces last chapter in chapter 3 to sort of do harder problems. Okay, so that's kind of the deal. So basically the notes are just going to be examples. Like, here's how you solve these kinds of problems. But really no new definitions or anything, okay? Cool. All right, let's do it. Here we go. We got 3 examples today. 2 of them you have on your notes, and then today, during my planning period, I realized we needed 1 other example. So we're going to do a 3rd one that you can probably fit on the page there. All right, so here we go. So force is a vector, all right? Again, as I said last chapter, everything we did is either horizontal or vertical, but in the real world, that doesn't happen. So in this example, it says, suppose a lawnmower has a mass of 40 kilograms. If we assume the wheels to be frictionless, and Roy pushes the handle with a force of 90 newtons at 50 degrees below the horizontal, then make a free body diagram and find the acceleration. Okay? So, thank you. All right, so these problems, you guys, they're going to start pretty much the same way as what we've been doing all along, which is every time you make a free body diagram, the first thing you should do is deal with mass and force of gravity. So that's where I'm going to start, all right? So here's my lawnmower. So I know that this thing has a mass of 40 kilograms, and I know that gravity is pulling it down. So I'm just going to put a little arrow here. Force of gravity is negative 392 newtons, right? It's 40 times 9.8. Cool. So that's always the first thing you should do. All right? The next thing we want to do is deal with any given forces. All right? So it tells us that Roy is pushing this thing. He's pushing the handle. As you can see, the handle's, kind of at an angle. And as a result, the force that he exerts is at this kind of angle. All right? Now, the directions do say to make a free body diagram, and at the end I will draw a complete free body diagram, okay? For right now, though, I just kind of want to solve the problem. We've got to find the acceleration, right? Everybody point for me, if assuming that the lawnmower accelerates, which it will because there's no friction, which way is it going to accelerate? This way, right? But Roy's force is this way, right? So we need to find a way to deal with that, all right? So what we're going to do is exactly what we did when we did vectors, which is we're going to take that force vector that's at a weird angle, and we're going to resolve it into its components. All right, we're going to find the components. So somewhere off to the side, draw yourself a little Roy vector. Here's the force of Roy. And it tells us that it's 90 newtons at 50 degrees below the horizontal. So drawing a little coordinate system. Oops. And then here's my 50 degrees, right? Not drawn to scale. Cool. So what do you think we should do? We can do some trig, but before we can do the trig, we need a triangle. So here's the force of Roy in the x direction. Here's the force of Roy in the y direction. And we are going to do some trigonometry. I'm never going to say that again that way. I apologize. Here we go. Force of Roy in the x direction is Fr times the cosine of theta, which for us is 90 newtons, times the cosine of 50 degrees. And that gives us a number that I've written on this piece of paper right here. It gives you like 57.851. I'm just going to call it 58 newtons. I don't know if you guys remember when we did forces, what I told you guys was to keep some extra, I've been calling them insignificant digits. Keep a bunch of extra digits and don't round until the very end. Okay? I mean, ultimately, as long as you've got the right idea and your answer is ballpark what I've got, then we're good. I really wish I'd spent a day at the beginning of the year talking about significant digits, and for whatever reason, I feel like at this point we haven't done it, so we're going to just muscle through. There was a hand up, Margaret.
Would you please explain to me where you got those numbers again?
The 90 and the 50?
Yeah.
Why
is it set up like that?
I gotcha. Okay. Thank you for asking when you didn't understand. So, I mean, we've got this triangle, and we know the length of the hypotenuse, and we know the angle, right? You good with that?
Oh, wait, no, sorry. I thought that the 90 was from the angle, and I couldn't figure out why you had a 90.
Are you good?
Yeah, I see.
So that's the hypotenuse times the cosine of the angle gives you the horizontal component.
Okay.
Good? Is everybody good? Does anybody want me to go through it? I'm happy to. I'm going to keep going then. Awesome. All right. So we found our force of Roy in the x direction. It turns out to be right around 58 newtons. And then similarly, we should find the force of Roy in the y direction. So the force of Roy in the y direction is going to be the force of Roy times the sine of our angle, which is going to be 90 newtons, times the sine of 50 degrees. And it gives us 69 newtons, sorta. Why did I say sorta? Yeah, it's rounded, but there's a bigger sorta. Ooh, negative, right? Which way is the y component pointing, you guys? Down. So, is everybody good with what I did then? All right, so if you're given a force at some sort of weird angle, almost immediately, you can probably guess that you're going to need those components. So it's probably worth your time to find the two components. Okay? All right. So. Move all this stuff over here. Okay, so now, what I'm going to do then is, again, technically my free body diagram should have Roy's force at a weird angle. And I'll make that drawing in a minute. Before I do, I want to kind of figure out what's going on with the object. All right? So what I'm going to do is I'm going to replace Roy's force with this horizontal and vertical component that I just found. So the horizontal component is this way. Force of Roy in the x direction is 58 newtons. Force of Roy in the y direction is negative 69 newtons. Cool? All right, now, you guys all pointed for me a minute ago. I said, which way is the object going to accelerate? So which way is it going to accelerate? That way. That means that my net force also has to be that way. All right, your net force and your acceleration always point in the same direction. Okay? So vertically, is the lawnmower going to accelerate?
No.
No. So watch what I'm going to write. I'm going to write net force vertically is 0. So now I can put in my normal force. All right? Something that we talked about towards the end of last chapter that's going to be super mega colossally important this chapter is when you're dealing with your vertical forces, the normal force is the last one you do. Okay? Because the normal force will be affected by both gravity and any other external forces, like Roy pushing down on the mower. So my normal force needs to be big enough to compensate for both gravity pulling the mower down and Roy pushing the mower down. Follow? And so it turns out that we have a normal force of, is it 471? 461? Yes. All right. Does everybody understand how I got that normal force? Or maybe I should say, does anybody not understand how I got that normal force? Okay. Now, since our net force vertically is 0, that means that my net force just depends on the total of the forces horizontally, right? Does that make sense? If there's no net force vertically, then if there is a net force, it's just whatever's going on horizontal. Say that one more time. It's only
if the object it's on is moving.
oh correct. Yeah, correct. Very good.
What if you're on a slanted surface as well?
That we're learning that. That's coming. I think that's tomorrow's not. It might be the next day. No, it's tomorrow or Wednesday. Okay. The problem said that it's frictionless, so we don't have to worry about friction. That's the other side. We're going to deal with friction. Okay. So because it's frictionless, this is it. These are all of my forces, right? So what's my net force going to be? Just 58 newtons. So now I can find my acceleration just by doing net force over mass. And so my acceleration is going to be the 58 newtons that are pushing it horizontally, divided by the mass of 40 kilograms. And you got like 1.45, completely ignoring significant digits, meters a second squared. All right, cool? Well, it's actually 1.448. Yeah. That's it. Okay, so are we good? All right, so really we haven't done anything new, right? It's just sort of like, oh, now we've got these weird forces to deal with, but we already know how to do it, so now we're just doing it. Cool? All right, if you flip the sheet over, it's basically the same example, but I put friction in it, okay? So, any questions before we go on to the next example? Everybody's good? Oh, no, I lied. We didn't finish this. What didn't I do? I didn't make my free body diagram. All right, so let's do that real quick. So the free body diagram, technically speaking, when you make your free body diagram, you don't put in the components, you put in the actual forces. So this is what your free body diagram would look like. You draw your lawnmower. Again, technically you should just draw a dot, but I don't like that, so I don't do it. So our force of gravity is negative 392 newtons. Our force of Roy is 90 newtons. Since it's at an angle, we should identify the angle, so 50 degrees. And then you've got a normal force of 461 newtons. There's your free body diagram. Yes? No. I feel like I should say more than that. Anytime two objects come into contact, no matter how smooth they are, you're still going to have the molecules rubbing against each other or whatever. The only way you can completely eliminate friction is to completely remove the contact. So the way they would do it in a lab is, I'll get you in 2 seconds. The way they would do it in a lab is they would use like an electromagnet or something to make the thing float, and they would have to do it in a vacuum. Cool? Yeah.
How do you set your calculator back to degrees? Because my stick was
Yeah, you got it.
mode.
Mode, yeah. All right. So this is what the actual free body diagram should look like, but it's sort of less helpful, right? Because when you look at this, you can't look at this and go, oh, well, that thing only has acceleration horizontally, because this drawing doesn't show me that the vertical force is canceled, right? It does show me that there's a net force this way, but it doesn't show me that there's no net force up and down, right? So this is the sort of the technical way to make your free body diagram, but I just don't find it as helpful as the drawing we made here with the components. Follow? All right. Any questions? Awesome-tastic. All right. So on the back, same problem, but now we got friction. So it actually ends up not being that bad. But the part that I'm going to add, the third example, does turn out to be that bad. So prepare yourself. All right, so here we go. We got a 40 kilogram, I almost said refrigerator. What do you call this thing? Lawnmower. 40 kilogram lawnmower. All right? Gravity's pulling it down. Roy's pushing it horizontally with a force of, was it 68? 58 newtons, thank you. Force of Roy vertical was negative 69 newtons. Normal force is positive 461 newtons. So that's sort of where we left off in the last problem, right? Sure. So I will let everybody get caught up there. Once you're caught up, think about what your next step is, knowing that there are now coefficients of static and kinetic friction That doesn't help at all, does it?
No, I like it.
Doesn't help a little?
I like it. Yeah.
All right. So, what do I need to add? Or what? I guess maybe I should say, what do I need to do? Good. Calculate your maximum static friction. So that's going to be our coefficient times our normal force. So let's see, the coefficient of static friction is the 0.6. Our normal force is 461. Let me pause for a minute. Oops. First of all, because I wrote that wrong. Secondly, notice the fact that Roy is pushing at an angle affects a lot of things. First of all, it means that not all of the 90 newtons of Roy pushing goes into making it move, right? All right. Secondly, inadvertently, maybe not inadvertently, but indirectly, he's making it harder to push the mower. Why? Because when he pushes down, if he wasn't pushing down, the normal force would only be 392, wouldn't it? But because he's pushing down, the normal force goes up. Like the normal force is bigger. Right? Thus making it harder to slide, right? Okay? So the force of the maximum force of static friction in this example ends up being like 276 newtons. Not sure if it rounds up or down. I did a rotten job with my numbers here. I'm going to call it 277 newtons. It might be 276. Is it 77? Okay. All right. So now, to see if it moves, I think no matter which number you pick, the 277 is going to be too big. But what number do I want to compare it with? With the 90 newtons?
No.
No. With what? The 58 newtons, because if it accelerates, it's going to accelerate horizontally. And it's this horizontal 58 newtons that would make that happen, right? Follow? So because 58 newtons is less than 277, it doesn't move, so how do I finish the drawing? Force of friction static, how much? 277? Negative 58 newtons, and it doesn't move, right? Cool. All right. So sorry, I'm thinking about what I want to do. All right. So is everybody good with this? All right. So this isn't going to move. And part of the problem is that Roy's force isn't very big. The second part of the problem is that because his angle is 50 degrees, sort of more of his force is going into pushing it down than is going into pushing it forward. See what I'm saying? Right? So that's sort of problematic. And it turns out that even if you increase the force, and I haven't done the math on this, but my intuition is that even if you increase the force, it won't ever move because pushing down increases the normal force more than it increases his horizontal force. Okay? That might not be right. I should sit down and do the math. But anyway, there's an issue there. So, is there something that he could do that instead of making the normal force bigger, would make the normal force smaller? What are you thinking, Max?
You could push 50 degrees above it.
Good. Yeah, instead of pushing down on it, what if we pull up on the handle? Right? Because then his force that is pushing it down into the ground is now pulling it up off of the ground. Not literally pulling it off of the ground, but he's sort of lifting up on it, taking some of the weight off of the ground. Like last chapter, we had that problem where there was, I don't remember the numbers, but whatever, a 300 Newton box, and somebody tries to lift it with 100 Newtons. Right? Doesn't that lessen the normal force? Okay. So, then the question becomes, all right, well, what if instead of pushing down at an angle with 90 newtons, what if he pulls up at an angle with 90 newtons? It turns out it still doesn't move because 90 newtons isn't that much force. So what's the obvious question? How much force do you need, right? All right, so here we go. Here's the last question. We'll do this in a different color. All right, suppose Roy pulls the handle at 50 degrees above the horizontal. This is an abbreviation I'm going to start using frequently. ATH is above the horizontal, BTH is below the horizontal. Okay? Because it's going to come up a lot. All right, so instead of him pushing it, he's going to pull the handle this way. And the question is, how much force does he need to get the mower moving? Sorry? Yes. Yeah, so it's a continuation of the last one. So. All right. This is a hard problem. This is I mean, you guys all know enough to do it, but you really got to think. There's some fairly serious algebra going on, and it's going to take a little work. All right, so any questions before we go on and try to solve this thing? Okay, so here we go. So here's the lawnmower. Now let me give myself a little more room. You're going to need some room to write some stuff up above your drawing, so don't jam your drawing up here. Give yourself a little room to work. All right, so here we go. 40 kilograms. No matter what, what's the first thing I should do? Force of gravity. So here we go. Force of gravity is negative 392 newtons, right? Now, Roy is this time going to be pulling this way, right? And that's going to have some, horizontal component and some vertical component, right? Now, our goal is, the problem here is we're trying to find Roy's force, right? So as much as possible, I want to write everything in terms of FR, Roy's force, okay? So, I know this angle is 50 degrees. Let me finish my train of thought here, and then I'll get your question, Ian, okay? You sure? Okay. So, Roy's force in the x direction is just going to be FR times the cosine of theta. And his force in the y direction is just going to be FR times the sine of theta. Follow? I guess I should say real quick, I don't know if this is messing anybody up. I assumed that the handle was still over here and he was pulling this way. There's no reason why you couldn't turn it around and have him pull this way. Right? Because it's sort of irrelevant whether he's pulling right or left. What's important is up or down. Okay. So, questions so far? All right, so here's what makes this problem kind of a pain. What's going to resist the motion of the lawnmower? What's the name of the force that resists the motion? Friction, right? And specifically, what kind? Static, right? And static friction, remember, we got to overcome the maximum static friction, right? Well, that depends on the coefficient, which is 0.6, and the normal force. But the problem is, depending on how hard Roy lifts, that's going to change the normal force, isn't it? You see what I'm saying? So, let's sort of put in as much as we can. So here's what we know. We know that this force over here, FRX, is FR cosine theta. And we know that the y component of that force is FR times the sine of theta. I'm sorry? Oh, yeah, totally, yeah. All those thetas are 50 degrees. 100%. Why am I not writing them in? I don't have a good answer for that. So if you want to write in those 50s, totally, let's do it. Yeah, no, you're right. Okay, so, who was that? Margaret, was that you that was saying that? Sorry, I was looking the wrong way. So, but yeah, Margaret's exactly right. Don't be intimidated by these sines and cosines. Sine of 50 is some number. I don't know what it is, but it's a number, right? And similarly, sine of 50 is some number, or whatever. I think I said the same thing twice, but you know what I mean. Are we good? All right. What other forces are there? Friction. So I'm trying to overcome my force of static friction maximum, right? Well, that's equal to my coefficient of static friction times normal force. Ugh. Why am I saying ugh? We don't know the normal force. So I think we can come up with an expression for it. Because look, suppose that this y component here, Roy's force, the y component, suppose it turns out to be, I'm just going to make up a random number, 92 newtons. Then what would the normal force be? 300. Doesn't the y force, Roy's y component, and the normal force, don't these two things need to add up to 392? So that means my normal force is going to be 392 minus whatever Roy has. There's no significance to the fact that I drew this arrow a little longer either, by the way. That's just because I don't know which force is bigger, right? All right, so let me pause for a minute. There's a lot of letters on the board right now. Are we okay with kind of the train of thought that I followed here? All right, so now we got to do one last substitution, which is this mess here is our normal force, right? So let's plug that in for our friction force. So that our force of static friction now is our coefficient, which was 0.6, right? Times this normal force of 392 minus FR sine of 50. Holy cats. A lot going on there. All right, we're done with the hard part. From here, it's just going to be a bunch of algebra. So, before I do algebra, are there questions about what we've done thus far? Everybody good? If you got questions, ask, because I guarantee you're not the only one. Everybody's good? All right, now, in order to get this thing to move, what needs to be what? The two.
Force used to be 277 to overcome.
Okay, so but that 277 was dependent on the normal force that we found in the last one, and that normal force was dependent on the 90 newtons. So that 277 that we had in the last problem doesn't apply anymore. So everything we need is on the board. There are no numbers that we need that aren't on the board right now. We're trying to get this thing to move. So, got an idea, Seba?
Sort of.
What do you tell me what you're thinking?
The normal force needs to be equal to the maximum friction thinking about it.
You're warm.
Okay.
But the normal force is up, and the friction is to the right. Those things will never be equal because this, by definition, is 0.6 times the normal force. Which everybody point. Well, sure, Joe. What do you got?
Roy X needs to be the same as.
There you go. Yeah, look, if we want to get it to move, we need Roy's force in the x direction to be bigger than our maximum static friction, right? Wouldn't that make it move? All right, so let's do this and see if we can make it work. Yeah, the greater than or equal to. Yeah, that's sort of like a weird nebulous region. But yeah, we want the force of Roy in the x direction to be greater than or equal to the force of friction static max. So let's plug in our numbers. Let's see. This is FR. That's an R. Ooh, there's someone at the door. What do they want? Hey, how are you? Oh, okay. So we need this FR cosine of 50. That's got to be greater than 0.6 times 392 minus FR sine of 50. And solve it. Does that make sense? All right, so let's go through the algebra. I'm going to leave the cosine 50 and the sine of 50 so that I don't have to worry about rounding later on. So here we go. So let's you got to either divide both sides by 0.6 or distribute the 0.6. Do it however you want. FR cosine of 50 is greater than or equal to, if you distribute, you get, is this 235.2? Minus FR times 0.6 sine 50. So all I did there was distribute the 0.6. Strange noise from the hallway. Okay, so now, algebra, what do I want to do? I want to get FR needs to be all on the same side. So let's add FR times 0.6 sine 50. So you get FR cosine of 50 plus FR times 0.6 sine 50. That's going to be greater than 235.2. This one's crazy, I know.
Could you just like migrate?
Oh, too many people? What's up? Mark?
Could you just like find the numbers for cosine?
If you want to, yes.
I'm sorry, I'm just curious.
Yes, you 100%. If you want to replace cosine of 50 and sine of 50 with numbers, 100% do that. Yes.
I'm sorry, where did we get 235.2?
So we've got 0.6 times this whole mess here,
Oh,
right here. So I distributed the 0.6. So 0.6 times 392, and then 0.6 times this. Make sense?
alright, yeah.
You good? Right.
Yep.
Everybody good? All right, so we're almost done. Woo! What can we do with this? I agree. Woo! We can factor out an FR, right? I just said factor. I said the F word. And it's on video. It's on YouTube. Will be. Take that, YouTube. Force. Oh wait, no, factor. Sorry. Never mind. That was funnier in my head. Okay. Okay. All right. What's my last step? We got FR times some big number. So divide by the big number, right? So my force of Roy has got to be bigger than 235.2 divided by this huge mess, cosine of 50, whatever that is, plus 0.6 times the sine of 50. So, Margaret, the reason I left those is just because as soon as you type in cosine of 50, that's going to give you some irrational number that goes on forever. And this just meant that I didn't round until the very end, is why I left everything. If you did it earlier, it's fine, I don't care. All right, so anyway, solve this, and it gives you... What do we got? 213. There you go, Roy's force. All right. But what I want you guys to understand is when you have that force at an angle, it snowballs, right? Because it affects all these things, right? Because the angle is going to determine the horizontal force that's trying to get it to move. It's going to determine your normal force, which is going to affect your friction, right? So there's a lot of pieces that fall into this. Questions? All right. I think this is harder than anything that's on the homework. And this is something that theoretically you should know how to do. Yes, sir.
Can you like technically not round down in this scenario since you're trying to find something that's larger?
That's a really good point.
Well, split the decimal.
So I've been really sloppy about my significant digits. I've been really sloppy about my significant digits. So it's kind of a moot point. So yes, I mean, I guess you're right. That to be safe, you should round up. That's sort of not the way that it's usually done, though, because then it gets a little bit too much into semantics. So. All right, are we good? The bell's gonna ring in like a minute, I think, isn't it? I mean, yes, you can.